Good morning, and first of all, welcome to São Paulo and to IFT. I'll take a few minutes to talk a little about the school. It's a pleasure to have all of you here, and this school has started back in the 70s when this institute was founded. Later, when it became a part of the State University of São Paulo, we renamed it Journeys into Theoretical Physics. I mean, actually the Portuguese version of that, and this one would be edition number 30 of that school. So it's been going on for a long while. Many of our best students have come through this school before joining IFT, either for a master's or a PhD. So I invite you all to profit from the lectures, of course. We try to provide you with good speakers and very interesting lectures, but also take your time here to get to know the institute, talk with the professors, and see our activities here. Two floors down, you can find the students from IFT, I mean the student room. So you can go there, try to talk to people. They will give you a first-hand experience and what it is to work here and study here. There are not many of them right now because we are not in vacation time, but you'll find some. I see some in the audience. You'll eventually find who they are. In terms of practical things, you can talk if you have problems with the hotel, bureaucratic stuff. You can talk with the secretaries. You all already met them. They stay in the first office in the corridor, close to the stairs. Right? If you need to, if you're looking already have in mind some professor you would like to talk with, they'll be around in the coffee breaks, but you can also, if you don't know the face of the person, there are some pictures right besides the elevator that you can look for and know the faces. And if you have any doubts, you can look for me. I'm Ricardo. The two other organizers, Nathan and Pedro, are here too. And don't be afraid to ask questions. Don't be shy. Try to mingle as much as you can and get to know the place. Later in the afternoon, we'll have a short presentation of the graduate program, both here in IFT and in Perimeter Institute. Right now, we're starting a new edition of this school that will be more international. We're having this interaction with the Perimeter. So you have a presentation about the lines of research, both in IFT and Perimeter, and some introduction to more practical matters if you get interested in want to join either of these institutes. You have some orientation in regards to that. So we'll start with the first lectures by Eduardo Ponton. I will let him go.
Thank you, Ricardo. So again, welcome everyone. We're happy to see this the attendance. As Ricardo said, my name is Eduardo Ponton. I'm a professor here at the IFT and ICTP-SAIFR. And so I will be giving 4 lectures on particle physics, one of the 5 topics you will be hearing about. And hopefully this will be an interesting experience for you. I think we can promise it will be intense, but I hope you will be able to learn quite a bit by the end of this week. So I'm a particle physicist, of course, and I don't need to tell you that particle physics is a very broad subject, and so that means that of course I wouldn't try to tell you or give you every view of particle physics. That would not be doable in 1 week, nor desirable. Okay, so I had to make some choices as to what I want to teach you, and that means that I have left out many things that are very interesting and important subjects even within the scope of particle physics. And I should also say that the way I'm approaching these 4 classes are really as lectures where I will try to go slowly enough and give you enough details that you can follow the arguments and So you will see most of the derivations I have provided. You will be able really to follow just by staring at the slides. I have perhaps simplified sometimes in order to make it make more direct arguments, but I think I have tried to keep all the main points. There may be a couple of places where you may need to perhaps sit down at the end of the evening and spend 10 minutes to fill in some steps. There might be 1 or 2 points where that would require more work, but those in general will not be essential to understand the development of what I'm going to tell you. So my choice was to try to focus on what one can describe as the latest very important development in particle physics, which was the Higgs discovery in 2012, 4 years ago. So that's okay. I was thinking, so 4 years ago is already, time passes quickly, and I was thinking that for guys like you, 4 years ago probably you were just starting to get into physics, so of course time passes much more quickly at your age, okay? So I don't know, but perhaps I'm hoping that nevertheless you were aware of the headlines in the newspapers about the discovery, or you've heard some things afterwards and are somewhat curious to know what this was about. So my goal will be to try to give you enough background to understand what the Higgs discovery was about, the Higgs boson discovery, and why it is an important landmark in this area of research. Now, to do that, I have to review for you. Yes. Yes, thank you very much. So the slides, so I will be using slides for these lectures, and they will be put online. So in particular, that means that you don't have to worry about taking notes. So just can concentrate on paying attention. Thank you. So I was saying that I will have to cover a few important ideas and conceptual ideas that are just necessary to explain what Higgs physics is about, okay? And so we'll be spending some time on that. But actually, before that, I thought it would be important to try to give you a more precise feel for what this physics is about before we dive into technical, perhaps somewhat or sometimes abstract concepts, because what we're talking about is something very concrete. Okay, it has to do with experiments. Physics is an experimental science, and the development of the standard model of particle physics that we have it was essential to have this experimental input. So I will actually spend also about half of the lectures just trying to convey to you what we are really talking about, okay? So the plan for today is to concentrate on what these lectures are about, and you'll see what I mean. And then tomorrow I will also spend time describing to you how we know, at least at the 0th order level, what we know, okay? And that's just to make sure that even if you are interested in theory, that you have a touch with the experimental background, okay? So let me start. So the first thing, of course, is I'm talking about particle physics. And so this can mean different things for different people, okay? So for instance, if we look at, I don't know if you can all see, but so this is an installation by a visual artist, Bex Andrews, who, inspired by the Higgs particle, came up with this gold dust, okay? And that's a fine interpretation of what one may mean by a particle. Or somebody else, like our director Rogerio, who's standing up there, may be interested in cosmological scales, where each of these dots, which is really a galaxy, is really treated as a particle. And that's perfectly fine if you're interested in those kind of questions, okay? Or we can now photograph today atoms, like these atoms here, right? So this is now the other extreme, the very small. And again, so all of these are examples of things that one can describe as particles, and nobody can tell you you're wrong, okay? So you should be asking really first, what do you really mean when we say particle physics? And what we mean by particle physics typically is the realm of subatomic particles, okay? So by some more or less arbitrary definition, atoms are not generally thought as being part of the particle physics studies, but things smaller than that, okay? And one thing that is important about this definition is that quantum mechanical effects are an essential component in the description of this physics, all right? And so I want to start to emphasize some points that will be important as we go along. I will go back all the way to the beginning of quantum theory, basically, and so recall some points. And this is not going to it's not meant as a historical review, but rather I will be able to present to you a number of concepts that you will see will turn out to be quite useful when we address, let's say, the more modern developments. So let's go to Planck's law for black body radiation, okay? And I expect that all of you have read and encountered this in your studies on quantum mechanics. So very briefly, what you have is you have a box filled with electromagnetic radiation, which is in thermal equilibrium with the walls at some temperature T. And the question at hand is, what is the average energy contained in these electromagnetic waves in some frequency interval between omega and omega plus d omega, okay? And Planck's law is this expression that I'm just giving you here as to remind you of it. We're going to use this in a moment. Omega is the frequency, h bar is the reduced Planck constant, c speed of light, v is the volume that you're considering, and so this is just a picture, not as a function of frequency, but wavelength, and so this has some particular shape. Now this law can be written in a more transparent way as follows. If we define this dn of omega in this way, which has if you think about it, this is one of those, let's say, 5-minute exercises that you sit down and you will understand. This can be interpreted as the number of modes, electromagnetic modes in the volume V, and with frequencies between omega and omega plus d omega. So that's just the number of modes. And this factor here, we recognize the 1 over e to the beta h bar omega minus 1 in somewhat more modern language as the Bose-Einstein distribution. And h bar omega then would be the energy of a photon, a quantum of the electromagnetic field. Now, I'm not really interested in how this gave rise to quantum mechanics and so on, but rather I want to jump 9 years and to an observation made by Einstein in 1909, where he argued on very general principles, statistical mechanics principles, that if you took this law at face value, and he had every reason to do so because it was a very good phenomenological description of observed data, okay, so that it was a fact in that sense. So he was interested not just in the average energy, but in the energy fluctuations, the mean square energy fluctuations. And he found that these mean square energy fluctuations consisted of 2 terms which are qualitatively different. The first one depends on the average energy quadratically. The second one depends on that only linearly, okay? And because actually the derivation of this formula is very simple, and also to so that you see that this was a very general argument, let me quickly go over that, for which I need to just review a couple of facts about statistical mechanics. So we start from the canonical partition function, z, which is just the sum over these Boltzmann factors. Beta, remember, is 1 over the Boltzmann constant times temperature. And the energies in your system, you sum over all of that. And from this definition, we see that if we take the logarithm of z and differentiate with respect to beta, what will happen is that when you differentiate the log of z, you get a 1 over z here, and then dd beta, I guess I forgot here the partial, sorry, you get, you just bring down an En in front, okay? So that what you recover here, you see is the sum of energies weighted by the Boltzmann factors. And this is precisely the definition of the average energy in this statistical sense. So this is very simple. I hope that everyone can follow and is fine with this. If you differentiate a second time this respect to beta, you see that what will happen is that there are, so this beta dependence in 2 places. There is a beta dependence here and also inside z. When we differentiate this one, we're going to bring down another factor of En and still normalize by z. So that gives an average of E squared. When you differentiate the z, you get a 1 over z squared and then the derivative, which is again a factor that looks like that. So you get the average energy, but now this squared. And that's a difference which is precisely the mean square energy fluctuation. So the upshot of this very simple argument is that you can obtain these mean square energy fluctuations just by knowing the beta dependence or temperature dependence of the average energy of your system. So what Einstein did was to simply apply this simple rule to Planck's law, like this. And it's a straightforward exercise in differentiation. But let me do it by looking at a couple of limits, which will be illuminating. First, if we consider the high temperature limit, or equivalently the low frequency limit, where this beta h bar omega is small compared to 1, then we see that this exponential here is e to the something small. We can Taylor expand. This is 1 plus that something small minus 1. The 1 cancels out. Then the h bar omega that came down here cancels with this, and we see that we just get this, a 1 over beta dependence times this multiplicity. All right? So we just have to differentiate with respect to beta, which is just this. If we do it, we get a 1 over beta squared, and then we see that this can be rewritten in this form as a square dependence on this same quantity in this limit. The other limit, which is the high frequency limit or a small temperature limit, in that case, this exponent is a large number, so the 1 can be neglected with respect to the exponential. And then the law reduces to this. By the way, I forgot to mention, the previous case was the famous Rayleigh-Jeans law. This one is called Wien's formula. But here we see that if we apply again this prescription, the beta dependence is here. We just bring down an h bar omega, and the rest stays the same. So we see that this is now can be written as something proportional to dE, to the average energy. And indeed, if you do everything without approximation, just differentiate here, you're going to find that the fluctuation is exactly the sum of these two terms. Now Einstein then, this is a very simple thing, but then he proceeded to interpret this result. So first of all, the quadratic term can actually be derived if you think of the electromagnetic radiation in your box as described by Maxwell's equations. It's a classical field. And so this is one of those longer homeworks if you wanted to do it. But believe me that you reproduce this exactly in that picture. The second linear term can be interpreted by making an analogy with a gas, an ideal gas of n non-interacting particles. So for example, in such a gas, the mean energy is given by 3/2 n number of particles kBt, which is just in terms of beta is like that. And if we apply the same statistical reasoning but differentiate it here, we see that in this system we also get something linear in energy. And Einstein gave other arguments based on momentum and other things to interpret really this as something that comes from something which is intrinsically a particle description. So this is where the concept of wave-particle duality was born. And to quote Einstein from that paper, the effects of the two causes of fluctuations, waves and particles, act like fluctuations from mutually independent causes. In other words, this additivity property here. And of course, there were many attempts to obtain this result from dynamics. In other words, trying to model your system and obtaining this average as not statistical averages, but as time averages of the dynamics. And what people found was that they were always able to recover one or the other term, but not both. Okay. All right. So I will come back to this example because it will be useful for us. But let me now jump to a more modern and standard description of this wave-particle duality, which is, of course, the two-slit experiment that, again, I expect all of you have seen in your quantum mechanics courses. And again, my point here is not to review that, but just to make a couple of points. So we have a light source, right? If we think of that as waves and they pass through two slits, you expect some interference pattern. But if you were to think of them as particles, photons, you would see on the screen dots, right? And I want to show you a clip of a modern setup, which is so it's quite amazing. Today you can really do on the lab something which is quite close to what is described in quantum mechanics textbooks. This will be short, so please be prepared to hear it narrated with a German excitement.
With a laser which produces light. This light is attenuated such that only one photon at a time emerges. This photon passes through a two-slit assembly, and then we have a camera which registers the pattern behind the two-slit assembly. So what we see is that the photons arrive one by one on the screen, some here, some there, and it looks pretty random.
Since the photons travel one by one, some through this slit, some through that slit, you would expect them to leave a pattern of two stripes on the wall. And you would be wrong.
So Morgan Freeman came at the end there to save the day, but I had to cut it off since it was about to get a bit too dramatic. In any case, so we see here on the screen, we start seeing the interference pattern. And interestingly, this same kind of experiment can be done with electrons instead of light, as indicated here. And what I have on this side, which I don't know how much you can see, but so these are photographs of an actual experiment where you send electrons by one, and you start seeing dots. There were a couple of dots here, which perhaps are not visible, unfortunately. But if you wait long enough, they reflect a statistical distribution with an underlying interference pattern, okay? So going back to our subject matter of particle physics, in terms of that analogy, we can say that particle physics experiments are such that we see particles when they resemble really, so we see them as particles, so they are more like the electron by electron part of the two-slit experiment. Nevertheless, we are interested in quantum mechanical systems, and like for the two-slit experiment, where we have learned that it is essentially pointless to try to predict where each individual electron would hit the screen, but rather what we can predict is the overall outcome when you repeat this many times. In particle physics experiment, we also do a setup where you repeat things many times, and we are interested in the underlying distributions in a number of particles. They don't have to be necessarily positions like in the two-slit experiment, but they are conceptually, it's a similar situation, okay? There is one important difference in the particle physics case compared to this other example, which is that the experimental conditions we're focusing on are such that the particles we are dealing with are often moving very close to the speed of light. So we're dealing with relativistic systems, okay? So from the perspective of a theoretician, what we need to be able to do if we want to describe these systems is to be able to compute quantum mechanical amplitudes that reflect, in particular, the properties of special relativity. That means, for example, that no inertial frame is special, or in other words, the laws we write down appear the same in any of such frames. There is a maximum universal speed. Nothing travels faster than that speed, and that is connected to a particular causality structure of this theory, of this physics. And also, the amplitudes that we're writing down, which are just, so at the end we're interested in a set of numbers, right? Numbers that depend on a number of variables, physical variables that we may have under control. But those are numbers, and they should allow a probabilistic quantum mechanical interpretation, okay? So this is what often we describe in fancy language as unitarity. So this is the challenge, okay, which is to write down quantum mechanical amplitudes that are consistent with this set of well-established principles. So quantum mechanics plus special relativity, that's what we're interested in, and this in this business has a name. It's called quantum field theory, okay? So quantum field theory is the natural language for describing this kind of phenomena, quantum mechanical phenomena where special relativity is important. And in later lectures, we're going to deal a bit into that. But just to be clear that it's not really optional, this is what we need to do, okay? Now, if we want to be a bit more precise, I could say that what we're doing is quantum field theory of point particles, okay? And a point particle, we understand that's something that has essentially no internal structure. So, for instance, it's defined by its mass, perhaps by a non-trivial spin, as you have seen in quantum mechanics. But certainly it could be that at a very short distance scale, what we call particles or elementary particles today, perhaps they have some structure, something more complicated. It could be little strings that are vibrating in some way, or perhaps something more complicated, and we don't know that, all right? So when we say point particles, I'm putting this in quotation marks because I'm certainly not, and nobody is excluding this kind of possibilities. We just don't know, okay? What we mean is that what we're describing are point particles as far as the resolution we have in our experiments, okay? So certainly, so it's at the end a matter of scales. If our probe cannot resolve something like this, then, and we're dealing with quantum mechanics and special relativity, then quantum field theory will be quite appropriate to describe those systems, okay? And this lesson is more general, so of course we can think of this sequence where we, so atoms of course are very small for our human scales. The nucleus here is much smaller, so if you're interested in atoms, the nucleus is for practical purposes a structureless point mass, okay? Even though we know that often they have lots of things inside, right? Nucleons, protons and neutrons. And we also know that these protons and neutrons actually are made of smaller things, quarks and gluons, but perhaps you don't have the resolution to see that, and then you will not care, okay? So these lessons is more general, as I'm saying here. Protons and nuclei can look point-like under many experimental conditions. Atoms, molecules certainly look point-like from our point of view, right? And quantum field theory can be used to describe any such system, okay? If you're in a regime where this is seen as you're not resolving the structure, it looks like a point particle, quantum field theory is perfectly appropriate. So in particular, I want to state very clearly that quantum field theory per se doesn't have anything to do with systems being fundamental or not. So this concept of being fundamental is at the end just a reflection of our current state of understanding, okay? Or just the interest, the resolutions we have. However, quantum field theory does become essential when we are working with energies such that particles can be produced, okay? If you have enough energy, because of the famous E equals mc squared, that energy can be converted into new particles, and particle creation can occur. That's a fundamentally relativistic effect. And so when you're dealing, say, with non-relativistic systems like a hydrogen atom, okay, you have your proton, very heavy, basically sits there to produce a Coulomb field, and you mostly concentrate on the electron, which is around. And even though you could describe this using quantum field theory, it's perfectly fine to describe each of those particles by introducing X and P's that describe these particles. But when you're in a relativistic regime, you must be able to describe the creation or even destruction of particles. Okay, so then QFT really becomes essential. Are there any questions? Okay, now let me, I want to go back now to the energy fluctuations story. And just want to make sure, so I expect that all of you have seen the harmonic oscillator, and in particular in this language of creation and destruction operators. Am I correct in assuming that? Or, okay. So just very quickly to establish or remind you of notation, and because we're going to be using this, so remember that the idea here is we have some Hamiltonian, which is quadratic in P and X. We just introduce new variables A and A dagger through relations like this, which allow you to re-express the Hamiltonian in this form in terms of the number operator. So we say we diagonalize the Hamiltonian in this basis. And these A and A daggers can be used to describe the energy states of the oscillator. So starting with the vacuum or the ground state, which we call 0, if you apply a dagger, you obtain a state that is the first energy state. And in our applications to particle physics, we will think of this as a one-particle state. Or you can apply a dagger n times with some normalization, and that will contain n such excitations. Okay. And so, of course, these are just the characteristic commutation relations that tell you that these A and A daggers are doing that they are creating or destroying these states and moving to a different level, if you like. So with this, let us go back to this relation I was showing at the beginning. So this had to wait until 1925 for a satisfactory solution given by Pascual Jordan. And what he did was to basically, just something that was well known, and all of you know, the electromagnetic field in a box can be thought as just a set of decoupled harmonic oscillators. Okay, so what he did was to apply the rules for quantization of a single harmonic oscillator to this system containing many. So let me consider a one-dimensional case, which is actually what he did. So this phi is a proxy for the electromagnetic field. Okay. And the point is that, so you have some expansion in terms of oscillatory functions, plane waves with frequencies omega n and wave vectors kn, that if you're putting this in a box of size L, they are given in some ways. They are quantized, in particular by the boundary conditions. There is a prefactor here that you recognize is precisely what appears in this transition in this part, so it's not quite surprising. And then he imposed these commutation relations on this system, which corresponds to the canonical quantization of the electromagnetic field. So it was a very simple procedure. It looks trivial from our point of view today. At the time it was less obvious. People were figuring out what they should do. But anyway, so you do this, and if you compute now the Hamiltonian, which in this system is something that contains kinetic energy, namely time derivatives of this field squared, as well as gradient energies like this, and just replace this mode expansion. There is a bit of algebra here, but believe me that what you get again is not totally surprising. You get a superposition of, so each, because each oscillator is independent from the other. For each of those, you're just expressing this in terms of the number of operator for the corresponding oscillator. So little n labels each of the oscillators in this system. All right. And indeed, what he did was to show that if you put this system treated in this way into a thermal bath at temperature T and computed the mean square energy fluctuations in a small segment, A small compared to L, he recovered exactly the two terms simultaneously. Okay, so this was the first dynamical way of obtaining both the, let's call it a wave term and the particle terms together. Okay. And indeed, this, together with the seminal papers by Dirac in 1926 and 1927, was what gave birth to quantum field theory. Okay, so this was the resolution of that puzzle, and the upshot is that the canonical quantization of a field, which is a continuous quantity, something that depends on the position x, okay, incorporates automatically the concept of a particle, so this discreteness. Okay. So this will be built into everything we do, because we're going to be using exactly this kind of language to describe the things we're interested in. So this is one reason why I go over this. Let me ask again, is that sufficient clear for everyone? If there are questions, I should say you should feel free to interrupt at any time. Okay, in addition, this formalism allows to describe the creation and destruction of quanta, which we call particles. And that's exactly the same game as for the harmonic oscillator. You just so we interpret, so there is a state, the ground state of the system that contains no particles. The creation operator on that creates a particle, a single particle in the universe. Applied twice, you have two particles in the universe, and so on. And when you include additional dynamics, you can start asking questions about is it possible to have transitions from an n particle state to some other n prime particle state? Okay, so this is a very simple way to describe this kind of processes where you create or destroy particles. Also, this was the application to the electromagnetic field, and so it was from the start something intrinsically relativistic. Okay, so we have that part. Now let me, I need to go over something else which I think is important, which is dimension analysis. And so this, I go over this also because you must have some sense of the scales that enter in your problems, okay? And so we need some references. So first thing is, so I remember when I was an undergraduate and I was told to think about dimension analysis, it seemed like a unit conversion, something boring and apparently pointless. But believe me, it's something important. We just have to be smart and try to simplify our lives as much as possible. So the first thing is to notice that there are a number of universal constants, like a universal speed has some value. There's a universal unit of action, Planck's constant, like this, also Boltzmann constant. And so this has, we're using here some units which are basically human units, which are stupid units if you want to describe these other systems. So instead of using those units, because we're interested in quantum relativistic systems, it's better to measure C and A velocities and action in units of C and H bar. In other words, we choose C and H bar equal to 1, and if you are interested in temperature, you can also set the Boltzmann constant equal to 1. So these are called natural units. And then the only thing that you have to remember, so everything will be measured actually in units of mass or energy, and the formula you must remember is just the Compton wavelength associated to something of mass m, which is h bar over mc. So this will allow you to, if you like, at any point, think of the scales involved, length scales or time scales, by using the speed of light, translate to the things that maybe you have been more used to thinking about. So let me give you some useful reference scales. So first we have, so first, one important thing is that most of the mass that we see around us actually comes from the proton mass, okay, protons and neutrons. And the proton mass is about 1 GeV. GeV is 10 to the 9 electron volts, or I'm just quoting this, 10 to the minus 27 kilograms, in case that's the number that you have seen before. So it's a small mass for human scales, but what will be useful to remember is that the proton mass is about 1 gigaelectron volt. The associated length scale is the proton wavelength, and if you use the previous formula, you will find that this is about 1/5 of a Fermi, where a Fermi is 10 to the minus 15 meters. As a comment, if you ask, so one way of describing how large the proton is to ask what's the charge radius. In other words, over what size is the charge distributed? And actually we know that, and this turns out to be about 1 Fermi. Okay, so it's something of the same order as this length scale associated to the proton mass. The size of the proton is very similar to its Compton wavelength. Okay, there is also an associated time scale to this, which is basically the time it takes light to traverse that length, and that's something like 10 to the minus 24 seconds, so very small. But these are the natural length scales that we will be dealing with. So dimension analysis, when we are working in natural units, is really just a question about thinking about mass scales, okay, which we can translate, if you like, to your intuition in this way. But I hope that you will develop an intuition directly in terms of mass scales. There is an important comment, however, that one should make, which is that sometimes dimensionless constants can have a crucial effect on the physics. So for instance, compared to the hydrogen atom, that again all of you have seen in your undergraduate quantum mechanics courses. So there basically we have a mass scale, which is the mass of the electron, right? So it's, of course, there's a proton and electron, but the proton is very heavy, so what matters is electron mass, or if you like, the reduced mass, which is basically the electron mass. The electron mass is 0.5 mega electron volts, which is about 2,000 times smaller than the proton mass. That means that its Compton wavelength is about 2,000 times greater than the proton Compton wavelength. Okay. However, if you remember what you know about the hydrogen atom, you see that the relevant energy scale in that system is rather E0, which is about 10 electron volts. Okay, quite different from this 0.5 MeV. And it's an expression like this, half alpha squared ME. And the associated length scale, which is the Bohr radius, is the electron Compton wavelength divided by alpha. Alpha here is the fine structure constant. So we see that the hydrogen atom is actually a big non-relativistic system due to this smallness of this alpha. In other words, so you see it's non-relativistic because just think of this as non-relativistic kinetic energy, 1/2 mv squared. So we see that the typical velocities of the electron are of order alpha in units of the speed of light, right? So it's small velocities. And it's much bigger than expected, and all of that is because there is this dimensionless parameter in that system that enters. So dimensionless parameters, we will not be able to put them in just by thinking about dimension analysis, but you need a bit more information, about how these constants enter into the dynamics of your systems. So this is a warning. So let me now go on to present the standard model. So our goal here will be to study some aspects of this. So this, of course, is the modern day version of the table of the elements, right? And I hope you appreciate that these tables are not just to be put on a poster and hang on your office. They do reflect some underlying structures, right? And they contain lots of information. So again, I will not be able to go over many aspects that are contained in this summary here, but I will go over a few. Let me just, okay. Maybe one thing that I can mention here is that these elementary particles come in different spins. All of these in violet and green here, they are spin 1/2 particles, okay? The ones in red are spin 1 particles. This one here is the famous Higgs boson, which is a spin 0 particle, okay? And those are just facts, observational facts, if you like, all right? They also come with different scales associated with them, different masses. And so, for instance, the heaviest of these is this quark here, the top quark, which is about 170 times heavier than a proton. these guys, the spin 1 guys, are also pretty heavy, 80 and 90 times heavier than the proton. And there are other things which are lighter. And a lot of physics does depend on these facts, which again, so those are things that you will not be able to get from quantum field theory. They have to be inputs to your theory, okay, to the standard model. But nevertheless, the actual physical consequences do depend on these things. Okay, we'll return to these things later on. For a moment, let me just mention that it is by no means the case that those are all the particles of interest in particle physics. Those are what we call now the elementary particles. But so let me just quickly go over the historical timeline. So the first of these particles to be discovered was the electron here in 1897. Somewhat later in 1919, the proton was discovered, in the sense that Rutherford convinced himself that there were protons inside the helium nuclei and other nuclei. Much later, in 1932, the neutron and the positron, the antiparticle of the electron, were discovered. Muons, pions, kaons. In the 50s and 60s, a whole plethora of new particles, okay, and more here in this second revolution in the 70s. And more recently, some of the spin 1 particles I described before, the W and Z. The top, discovered here in 1995. This timeline goes up to 2010, so that's before the Higgs discovery, which was in 2012, which is the one that we're heading towards. This was just a summary presented by The Economist that tells you the time that passed between the, let's say, the proposal or theoretical expectation of the existence of some particle and its actual discovery, okay? And we see the Higgs boson was the one that took the longest to find out, okay? And perhaps by the end of the lectures you will understand a bit better why this was the case. Another important thing that I need to emphasize is that the way we learn about particle physics mostly goes through a paradigm which is that of scattering experiments. And of course, this was pioneered by Rutherford here. I hope all know the story. He sent alpha particles, which are just helium nuclei, and they let them scatter into a gold foil and observe what happens. Some of them went almost through. They scattered by some angle. Sometimes they were scattered quite a bit. And he was just measuring basically this angular distribution, okay? Which again, in terms of the two-slit experiment analogy I was making, that should be thought as what makes the underlying distribution that we're interested in understanding. Now, of course, we know that what's behind this is essentially the scattering of these sort of charged particles via the Coulomb interaction. In this case, there are basically two parameters, which is the impact parameter and the energy of the incoming particle, and that determines this final scattering angle. So this is, of course, now well understood, and probably you have seen this in some classical, perhaps classical mechanics courses. But what is important here is that this illustrates an important way in which we have found out what we know about this table before. We have another interesting landmark here, which was the discovery of the electron antimatter, okay? And let me spend a couple of minutes here. So, of course, this was famously predicted by Dirac in 1931 and discovered experimentally soon after in 1932 by Carl Anderson. And this is the famous photograph that shows the discovery. Do you see the positron there? So there is an obvious feature, which is this track here. So these were rather clean things. So indeed, that is what was the positron. This came from cosmic rays, and the observation of Anderson was that cosmic rays contain both negatively and positively charged particles. Of course, at the time, protons, which are positively charged, were known, but he knew this was not a positron because the positron is much heavier and would leave a much shorter track, okay? So he saw particles with these characteristics. This was in some magnetic field that I'm indicating here, bending in both directions, all right? Now, given that I'm telling you that the magnetic field is like this going into the page, can you tell me that this is indeed a positively charged particle? I will give you 10 seconds to think. So you don't know in which direction it is moving, right? Huh? What? Which plate? Okay, so you know too much. Good. So there is this other big feature here, which is this horizontal thing. That is a lead plate that Anderson put in there precisely to try to distinguish that. The idea is that if there was a particle coming from some direction and it passes through the plate, it will lose some energy, therefore it will slow down, and therefore after that, the magnetic field will be able to curve it more, right? So this tells you that indeed this particle came from below here because the curvature here is larger than there, right? So with that, now you see that this is indeed a positive particle. So you know your Lorentz law? I hope so. All right. Anyway, so this was very nice, of course, very important. This will stabilize in a moment. So, of course, those were simpler times. This is an example of a so-called cloud chamber, which is basically a setup with a supersaturated vapor, such that if a particle which is charged passes by, it can hit some of the electrons in the vapor atoms, ionize those, and those serve as seeds for condensation in this supersaturated medium. And so they allow you to see really particles going through, okay? And this was used to observe many things. So for instance, here, this is a nice example. I hope you can more or less see. There you see these rays that actually have a finite range. These are alpha particles or helium nuclei. And this finite range business will be also of some importance in our later part of the story. Of course, things progressed, and the same techniques essentially, but using or similar techniques, but with higher energies, and you observe more complicated stuff. So you, in particular, we're seeing all of these are clear trajectories. We're looking at particles, right? That's what we have to describe. Let me show you one more picture of historical importance. This plate here was the discovery of the so-called neutral currents by the Gargamel bubble chamber in 1973. Okay, so there are many things there. Actually, the interesting part corresponds to these tracks, this part of the tracks here, which are interpreted as follows. So what they were doing in this experiment, so this is a bubble chamber that's, okay, I will not describe the workings, but it's another way of allowing us to see what went through. They were sending in neutrinos. Neutrinos are particles that interact very weakly. In particular, they are not electrically charged, so you cannot see them in a setup like this. You only see charged particles here. The neutrino was coming from up here, okay? So what you see here is that it knocked out a particle. And actually from the characteristics here, so this is a charged particle, it bends, there is a magnetic field. At some point, moving in this medium, it emits photons, a process called Bremsstrahlung, and those photons are still energetic enough to produce electron-positron pairs. And so these here, which bend on one side and on the other, are one of those. So the point is that here there are enough characteristics to tell that what you're seeing here is an electron, okay? It's an electron that was knocked out from the atoms here. And what was happening here was that so you also know that the neutrinos that they were using were what are called muon neutrinos. There are different kinds of neutrinos. These are muon neutrinos. So you have a muon neutrino or perhaps antineutrino, and there is an electron there, and there is an interaction between those two where this is scattered again like this, and this is, so this electron we're not seeing there, that was before it was being knocked out, but this is the final electron that we are seeing there, okay? And something is exchanged here, which we know as a Z gauge boson. There is another process here that they had seen before, which is, so this is called a neutral current. There is another process here, which is something like this. Let me draw it. Where you have an electron, which can convert into an electron neutrino. You have your mu neutrino, let's say mu neutrino, and this can convert into a muon, and what you're exchanging here is called a W, okay? These are called charged currents. So the signature here is that, so of course you don't see this neutrino, neither that one, those are both neutral, and you don't see them in this feature. What you see is something, a muon being knocked out, which is very different from an electron, they can tell, okay? So actually this discovery here was not the discovery of this Z and Z gauge boson. That happened, the Z and W were discovered about 10 years after this. But it was the discovery of these processes which are neutral. Their neutrinos do have interactions, even though they are neutral. And this played an important role in the establishment of the standard model as the correct description of this kind of physics. So let me finish now by, so this just, okay, I'm trying to show you various pictures so that you see what people are actually looking at, okay, and to give you a feeling of what is the thing that we want to be able to describe theoretically. Today, of course, what we have is the Large Hadron Collider at CERN in Switzerland. And so that's the biggest machine, the biggest collider we have constructed, which means that we can accelerate particles to the highest energies we have achieved in laboratory experiments. What we do there is we accelerate protons to beams of protons and to energies which are about today 13,000 times the mass of a proton, okay? And then you allow them to collide and see what happens. And that's the context in particular in which the Higgs boson discovery took place. So let me show you, perhaps, sorry, let me go back. Let me show you this animation just to explain to you a bit how this works. So actually, CERN is an accelerated complex. And so this is just to show how the process works. So we have there a proton bunch, say, which is initially accelerated by a booster to 1.4 GeV. There are two which will later collide. It's passed to another one, that the proton synchrotron, which is accelerates farther. They are fed into the super proton synchrotron that accelerates to 450 GeV, and finally to the LHC, where they are finally made to collide. So we go in there. Somebody wrote the standard model. We're crossing from France to Switzerland here. So this is the proton, and this represents the quarks inside the proton. So these are going to collide at in the Atlas detector. So the two collide there and produce stuff. They produce new particles, and the idea is to measure in different ways what is produced and try to interpret and get information that perhaps will take you beyond what you know at some point. So we have certainly come a long way in terms of how do you say, to showing these things. So this is made for the video game generation, I guess. But so we're going to actually later on see some examples of some actual events which are of interest, so that you have a feel also of how we read these things, okay, in this modern day way. So I will do that tomorrow. I will stop now. I'll just let you know that if you go to this this link here, you will find an LHC guide with lots of interesting information about the LHC. Okay, so I encourage you to go there to try to get an idea of what this machine is about, the numbers. There are some fun facts. So please, so as we said, we're going to post this thing so you can just use that to go it there. 1 hour. Thank you.
Could you explain more about neutral current and charge current about these decays, please?
So these are not decays, these are scattering processes, right? Okay, I plan to explain a bit more about this, but so what do you want to know specifically? It's an open question, right? So
yes, it's more about the charge current. Could you use photon in inspired W?
So the thing here is that the particles that you have to begin with, these neutrinos, are not electrically charged.
Yes,
so the photon does not contribute here. But indeed, there are processes. You can consider also scattering processes, let's say between an electron and a muon. Okay, that's a possibility. And then you will have different contributions. You can exchange a photon. You can also exchange a Z, right? And then, so this is one example where you have quantum or potentially quantum interference. You have to add two things in the amplitude to get the probability. You have to square the amplitude. And so, yeah, I will say a few more things about those kind of things later on. So the way to think about these pictures, there is physics here. I just wanted here to illustrate with these diagrams, which are kind of self-explanatory, this thing, but please.
Okay, thank you.
What's the difference between? Okay, sorry. So the Z boson there, what is it doing? Like I can't see. Like what's the difference of having it there or just the particle going and not changing anything? What is being changed there? Exchanged between the neutrino and the electron. I didn't get that. So this is so really what you have, let's say, in real space is you have a sitting electron in your chamber, right? And you're sending a neutrino, and you observe a neutrino, and this is knocked down, right? You have the going out the electron. So what the Z is doing the kick, right? So it's, and again, I will, so as I said, next time I will use the photon example to explain in a bit more detail how, so if you had, let's say, a process like this where you have electron, let's say muon here, scattering through a photon, how this does correspond to what you know about these interactions between charged particles. In other words, the Coulomb potential, okay, in the non-relativistic limit. So the Z or the W here are doing something like that. It's exchanging energy and momentum. It's the mediator.
What is the typical length of the bending of the curve in the bubble chambers and things like that? Because I think that needs to be more larger than the quantum wavelength, no? And how much?
It's macroscopic. You could see it.
It's
right?
macroscopic.
Yes,
okay.
yes. These are pictures, photographs of plates taken different ways that you could just see with your eye.
Naked eyes.
Yes.
Okay.
Not the LHC one. Okay. We'll go to that's a bit different technology, but all the other ones. That was one of the reasons I was showing them to you. Is something that you can go and see. You are seeing these particles.
Okay.
So the bending will depend on how much momentum the particle has. If it's too energetic, it will bend less, and it might be that you can barely see any bending. Okay. If it's going very slowly, it will bend very rapidly.
Okay.
But okay.
Can a fermion be its own antiparticle?
Yes. So this, so it can. Okay. One question is whether there is any such thing in our universe, and turns out that the neutrinos are potentially fermions that could be their own antiparticle, but we don't know for sure.
Why did you say that? What proof do you have of neutrinos in that case?
Why what?
Why do you believe that neutrinos can be potentially its own antiparticle?
So it depends on, okay, this ties down to the fact that neutrinos are known today to have non-zero masses, and there are two different types of masses you can think for fermions. One is called the Dirac mass, which is a mass that we have for electrons or muons. There's another type which is called the Majorana mass, which is a mass that you can write down for particles that are the same as their antiparticles. And even though we know that neutrinos have a mass, we don't know if they are Majorana or Dirac, okay? So this is a question of, so you see, particle physics and the Standard Model is all about establishing the degrees of freedom that are present in nature, okay? And that is something that we get from experiment. So far we don't have principles that tell you that you must have this or that and not that, okay? So the question whether these guys really have, they are two or so some degrees of freedom or twice that, whether they are the same as the antiparticles, is just not settled.
Hello. I would like to know in the wave function of the electromagnetic field, what is the HC that you put in the middle? I actually don't know.
Yes, transformation conjugate.
Okay.
And I will be using that.
Okay, I didn't know that.
Sorry, I should have said, certainly.
Okay. Thank you.
It was there. Yeah.
If we didn't know the theory about neutrinos and Higgs, do you think that we will find them anyway? Because they are really hard to find, and LHC was built to find them, find the Higgs, not neutrinos.
The question is, if we didn't know, so we didn't know the Higgs. So
we know the theory about neutrinos and Higgs.
We know much more than that. We know the theory about this many particles in the Standard Model. So neutrinos.
But the LHC was built to find the Higgs.
Yes.
If we didn't build the LHC to find the Higgs, do you think that we find it anyway?
Sorry, let me try to understand what he's asking, because so.
If we didn't build the LHC, you think we find the Higgs anyway?
Well, we need some machine to find. So the Higgs. Okay. So maybe let me answer this way, as we're going to see again tomorrow. So many of these particles are highly unstable. They are not present there in natural state. Okay. If they are produced, they decay fast. They disintegrate in other particles very fast. We're also going to see that the mass of the Higgs, now we know, is about 125 times larger than the proton mass. That means that if we're going to produce this thing, to transit, you need to have enough energy to do it. And to do that, we need a collider that does that. So whether it's the LHC or other machine, so you need some machine to produce the thing, and then, so we're going to, as we go on in the lectures, we're going to, the fourth one, I plan to tell you exactly how we saw the Higgs exactly, okay? But we need a machine to do that. Otherwise, yes, we will know.
No, having a machine is different than looking for something in that machine. We analyze the data differently.
So we have the, okay, so we built the LHC, and we knew enough to, again, we'll explain, we knew enough about the properties or the expected properties of the Higgs boson, so that we knew where to look. Okay, and in fact, the LHC was built and advocated with that in mind. Okay, so we knew all of that. So I'm not sure what's the parallel story that you want me to imagine.
It's because this is a big thing, because before quantum mechanics, we think in a Galilean way. We look the skies and the universe, and before and after we do the theory. But in quantum mechanics, we did the theory, and then we find some things. You know, we look for things, not.
Well, no, it's not always at all like this. I mean, so the Higgs boson, yes, it's a very special and anomalous case where that was the order of things. But there are many examples in the standard model of things that were observed first, and then in trying to describe them, you came with some theoretical ideas and models that, of course, you want to test. One of the ways to test them is to make predictions. In some cases, the predictions were that you should see some other particles, okay? And so the Higgs boson is one of those examples, okay? But so it goes both ways in many combinations, okay? You cannot control how history proceeds, but I'm not sure if you're trying to cast a doubt on what we are seeing, or so I'm not quite getting the gist of your preoccupation, but perhaps we can discuss later more, I don't know.
Oh, hi. Can that scattering happen with the positive W boson or not?
Yeah, so here, so they are, so this one, right?
Yeah.
So this I put here both. So if I'm thinking that I have an electron like this, if I think of this propagating with an arrow here, and think of this as a W plus, but I can equally well think of this as a minus. So one of them is the antiparticle of the other one. It's not, you can think one way or the other.
Okay, another question I have is that as we have touched the neutrinos thing, how would the annihilation of neutrinos work? Would they produce W's or Z's?
The scattering of the...
no,
so
annihilation with the neutrino and antineutrino.
Yes, so if they... Right, so there is a vertex or a process like... So if you, so like this, where this is an anti-neutrino and a neutrino, and there is this same vertex I have here with a Z, okay? Not a W, because W is charged, so you will not be able to conserve charge here. But, so here, so this is a massive guy, right? So, okay, so this, so you still, there's one thing that you must, the fact that this vertex exists is not sufficient. You must make sure that energy and momentum are conserved. And in a process like this, it cannot happen. So.
Anyone else?
Hi. When we talk about particle physics, we only talk about the scattering process. Are there any other experimental methods to measure particle properties used today, currently?
Yeah, so it depends on some. So for just to give you an example, so there are ways to search for some hypothetical particles, which are called axions. And so one of the properties of these axions is that they interact with the electromagnetic field. And what you do is you have a setup where you have a resonant cavity with electromagnetic waves, in the hope that you can produce there an axion. You can sort of convert some of this radiation to axions, and then it can travel to another cavity and detect it there. So it will be an example of a different approach.
Thank you.
In the table of elementary particles, I see that you didn't include the graviton. And some tables I've seen, and some tables I have seen.
I didn't include the graviton. This is the gluon. You mean up there?
Yeah.
It's not the graviton, it's the gluon.
Some tables that I have seen, they include the graviton. So
yes,
there is this difference, but it is an elementary particle. It isn't. It exists or it doesn't. What is the problem with graviton or gravitation in these energy scales that you
It is very weak at this, in all these processes. There is a difference between what we expect and what we have established experimentally. Okay, so gravitons, it's a perfectly fine way to think about gravity when you quantize it in a low energy regime. Okay, and so gravitons, the difference between graviton and the guys here is that they are spin 2 particles. And you can set up, so it's very similar, actually, okay? But seeing a graviton as a graviton, like as a particle, is extremely hard because it couples very weakly to anything else. So I guess that's the main reason why it is not included as, gravity plays essentially no role in these experiments. It is there, of course, but it is a negligible effect, and so that's why it's not displayed here.
If it exists, how would we find it?
I'd like to know.
So maybe we'll take a coffee break now, and we have another session of questions at the end of the day. So we have some question that can't answer. So let's thank Eduardo.
Coffee break is upstairs. You go up these stairs on the